Hello everyone. In this session, we are going to discuss about how to apply best first search for 8 puzzle problem searching. Okay, so there is an initial state given. An initial state will look like this. Any combination of the numbers. And what is an 8 puzzle problem? You will have 8 numbers in this 9 cells. Okay, 9 tiles or 9 cells. Okay, it is in 3 cross 3 pattern. And this has to be arranged in this pattern. This is a goal state. And the arrangement of numbers should be 1, 2, 3, 4, 5, 6, 7 and 8 with the middle tile as an empty tile. Okay, so this is the final goal state that is needed, and the operations that are allowed is we can swap this empty tile. Okay, so this empty tile can move to the up, like we can swap 3 and empty tile, or 4 and empty tile, or 6 and empty tile. Okay, so the allowed operation here is we can move the empty tile up or down or left or right. Okay, so these are all the possible moves that are allowed for each and every step. Now what we have to do is we have to first create a search tree. Okay, since searching actually is going to happen in a search tree, and first step is going to be creating a search tree, and it is a best first search, right? What is a best first search? It is an informed search method. So you should have a heuristic value. We should know how to calculate a heuristic value. There are 2 methods in which we can use a calculate a heuristic value. I'll teach you one in this video. And then the last step is going ahead with the searching pattern. Okay, so this process is like sequentially we have to complete it. So first of all, I'll start in constructing of a search tree. See, I don't construct the entire search tree. I'll stop it within a level. Then we can proceed on parallelly calculating the heuristic function for what all we have calculated, we have constructed, and then that followed by a searching algorithm too. Got it? So now first step, this is the initial state that is given, and there are 4 possible moves. But here, when the empty tile is in this place, I can just swap it with 3, 4 or 6. So only 3 possible moves are allowed into this category. Okay, so I have 3 branches for this. Okay, mentioning the next possible move. We have the same 3 cross 3 grid. Okay, so when I swap 3 and this empty tile, your pattern will look like this. 1, 2, 3 and empty tile is swapped. The remaining numbers will remain as it is. Okay, so this is one way of swapping. Just swapping this 3 and this empty tile. Or I can swap it with 6. When I am swapping with 6, your pattern will look like this. 1, 2, 3, 8, 7, 5, 4. Okay, and I can swap with 4 too. 1, 2, 3, 4 here and the empty tile here. The remaining numbers will remain as it is, 7, 5. Okay, so these are all the only possible move that are allowed to proceed with the initial state. After initial state, I can swap it with either 3, 6 or 4. When I swap with 3, 6 or 4, I get this pattern. Okay, so what I do, I try to construct one more level of search tree. Okay, since we have to include all possible conditions, I'll do one more level, and then I start constructing a customized version of this tree, and we can proceed with the searching algorithm too. Okay, so the next level is going to be like we have 3 states here, and here is the place where I can make it. Like I start from this node, so I can just create 2 different swapping here. I can either swap it with 2 or swap it with 3. So what happens if I swap it with 3? My pattern will look like this, right? When I swap 3 and empty cell, it will become 1, 2, 3, 8, 6, 7, 5, 4, and this is same as that of this initial state. Okay, so what I do for my convenience, when I have the same state to be proceeded, okay, I'll remove it. I don't use that. Okay, so the repeated tiles, I'm going to ignore it. Whatever is the unique tile I'm going to get, that alone I'm going to proceed on. So this, I'm going to create only one branch, The reason is the other branch is same as that of the initial state. Again, for that it will repeat the same process. So I just swap this with 2 alone. 8, 6, 3, 7, 5, 4. Okay, there are 2 possible moves. This is one possible move, and the another possible move will again generate the root node. Okay, so I'm not going to explore it again. So I just stop. When a tile repeat, I'm not going to expand it. Got it? And similar case over here. How many possible moves are allowed? I can swap the empty tile with 8, 6, 2 or 5. 4 possible moves. And out of this 4 possible moves, when I swap it with 6, it will create to the initial state again. So I'm going to ignore it. I'm going to add only 3 possible moves here. Okay, when I am swapping with 2, or I can swap with 8, or I can swap with 5. When I swap it with 6, it will generate to the initial state again. Okay, so the remaining numbers is 2 is swapped, 3, 8, 6, 7, 5 and 4, and here I have swapped with 8. So the remaining tiles are 1, 2, 3, 6, 7, 5, 4, and here I am swapping with 5. The remaining tile will be 1, 2, 3, 8, 6, 7 and 4. Okay, so these are all the children's or the next move I'm going to get out of this present state. Okay, and again the last step, I can just take this place, I can swap it with 4 or swap it with 5. When I swap with 4, it will generate a structure like this. It will create a node. Okay, where 4 will be here, empty space will be here. The remaining cells will remain as it is, 8, 6, 7, 5. And this is same as that of this initial state. So what I do, I ignore this. Okay, I'm not going to use this. I'm going to make a swap only with 5. When I make a swap with 5, my tile will look like this. Okay, with only one children, I'm swapping 5 and this empty cell. Okay, so the remaining node is 1, 2, 3, 8, 6, 4. All done. I'll stop the tree construction here. The next step is to find the heuristic function. Okay, so what function I'm going to use is, heuristic function is calculated with number of misplaced tiles. We can use man-handed function also. So in this example, I use the number of misplaced tiles, that is easy for us to calculate. So I'm going to compare each and every state with the goal state, and whichever tile is missing, that will be taken as a goal state. For example, in goal state, 1 has to be there in first place. It is same as here. 2 is also in the same place. 3 is also in the same place. Now here in this cell we want 4, but you have an empty cell. So this tile is not matching. Okay, so the heuristic function here is calculated as, h of this node is 1, 2, 3. 1, 2, 3 is in same place, but here in the goal state we want 4, but in the given example we have an empty tile which is not in the same position, and again mid position should be a empty tile, but here you have 6, that is also missing, and 8 is in same position, 7 is in same position, and here you want a 6, but in the given state it is 5, that is also misplaced, and the last cell should be 5 where we have 4. Okay, so we compare the present state with that of goal state and find all those misplaced tile. Okay, here you have 4 misplaced tile. So the heuristic function for this node is 4. And similarly, we have to calculate for each and every node. Okay, so consider this second step. Okay, 1 is in same position, 2 is in same position. But here you want a 3, it is not there. So 1 plus. Okay, I'll just put a into mark wherever it is not in same place. Okay, so here you want a 3 is not there, and here you want a 4 is not there, and here you want a 5 is not there. The middle portion should be an empty space, that is not there, and 8 is in correct position, 7 is in correct position. Here you want a 6, but we have 5. So these tiles are not matching 1, 2, 3, 4, 5. So the heuristic function for this place is 5. Okay, so similarly we have to calculate heuristic function for all the nodes. Here 1, 2, 3 same position, 8 and empty tile same position, this is not there, 7 is in same position, and these two are mismatched. So the heuristic function for this node is 3, and for this node it is 1, 2, 3 same position, 8 and 7 is same, and 4 is in same position. These 3 tiles are misplaced. Okay, so the heuristic function is 3. Over here 1 is fine, this is wrong, this is wrong, 8 and 7 is in same position, 6 is not there, you want a 4, we have a 3, you want a 6, we have a 5. Compare it with goal state each and every step. Okay, you want a 5 as the last tile, but we have 4. So what is the number of misplaced tile? It is 6 misplaced tile here. And over here 1 is in same position, not 2. 3 is fine, 8 is fine, mid position is not there, and this is not there. 7 is fine, these two not in position, 1, 2, 3, 4, 5. And for these two examples, 1, 2, 3, it is in Paka order as a goal state. You want an 8 here, then you want an empty tile here, you want a 4 here, 7 is there, and the 6 is not there, 5 is not there. So here also heuristic function is 5. And here 1, 2, 3 same position, 8 is fine, this is not in same position, 6 no, 7 is fine, this is not there, this is not there, so 4. And you have 1, 2, 3, 8, this is not in same position, 4, 5, 6, 7, this is not in same position. So the heuristic function for this is 2. Okay, so right now I have simplified it. What we have done so far, we calculated the heuristic function. Okay, first we try to construct a search tree, and then using the number of misplaced tile, we try to calculate a heuristic function, and the tree is not complete actually. Okay, you should know that we have stopped it halfway. Okay, so once we are able to complete your best first search, whatever is needed, we just expand that node alone. If you keep on expanding your tree will become a bigger. Okay, for your exam point of view, we cannot use that. So what I do, I'll just try to redraw this given tree into a new structure. Okay, rather than using the same, I'm going to give names for each and every state as S, A, B, C, D, E, F, G and H. I'm going to construct a new tree with the nodes like this: S, A, B, C. I have 3 nodes here, 1 node here. This is D, E, F, G, and here you have H. Okay, now the tree is simplified. I'm going to use the same heuristic value that is calculated. So starting from this, S takes value as 4, 5, 3, 3, and you have 6, 5, 5, 4, and 2. Okay, so now the next step is I'm going to run the best first search algorithm out of this tree. Okay, so with that simplified tree, I'm going to run this best first search algorithm. You know what is best first, right? I recommend you to watch this best first search video before coming here, so that you'll understand it better. Okay, I'll just keep it here. I don't want to mess it up. We have an open list and we have a closed list, might be extended. What is there in open list? Open list is made up of priority queue structure. Okay, that consists of all the nodes along with the heuristic function, okay, that are waiting to be explored, and closed list consists of all the nodes that are visited. Okay, so you'll have a node along with the heuristic function here, and a node with the parental. For the path problem, we'll have a parental structure here. A node and the parent will be added here. Okay, and how does it works? We start with the starting node as S. So S along with the heuristic function is added. When you start the process, what we know, when we start constructing this tree structure, we just know the initial state alone. Always the root node alone is known for the user. Okay, so what we do, this is your open list. or the priority queue, and we take the node with the minimum priority. Since we have only one node, we take this node S and explore S. What does exploration means, or we can call it as visit thing. Okay, so this is your visit list or closed list. All the nodes that are visited will be added over here. So what happened here is, when you are visiting a node, we have to find all the children of that node, add it to the open list. So S has a children as A, B, C. So this A, B and C will be added into the priority queue along with the priority value. Heuristic value is taken as the priority. Okay, so all A, B, C is added along with the heuristic function. What is the next step? You have to repeat the same process. Choose one node in the priority queue with the minimum priority and visit that node. Now what happened here? We have two nodes with the same priority. B and C have 3 as the priority, and that is the minimum priority too. So in this case, how to proceed on? We have to take a queue data structure format, first come first serve basis. So whichever node that is initially inserted, will be taking that and we are going to explore it. While adding it into the visit list, add it along with the parental node. For B, the parental node is S. Okay, when you are adding it into the visit list, what does visiting means? Find all the children of that node. So B is attached with 3 children, that is E, F and G. We are going to add all the children node along with the priorities as 5, 5, 4. Got it? So what is the next step? When you are adding this node, the next step is again to choose a node with the minimum priority. Okay, so one node is explored, B is explored, and we have added all the children. Now what is the next process? Out of the remaining all the nodes in the priority queue, we have to choose a node with the minimum priority. So the minimum priority is 3 and the node that is chosen is C. What is the parental node for C? It is again S. Okay. Now what is the next step? We have to explore C. When you are exploring C, find all the child node of C. C is attached with only one child, that is H, and we have to add that into the priority queue along with the priority function. Priority function for H is 2. Okay, repeat the same process. Out of the priority queue, the node with the minimum priority is H, so H will be taken. Okay, since 2 is the minimum priority, we are going to take H, and the parent of H is C, and we have to explore H or visit H. When you are visiting H, find all the child node of H. Now this is the place where we have to expand our tree. Okay, I told you now we have halfway completed your tree structure. We haven't completed it fully. The reason is, some point we might not need to expand and some point we want to expand it. For example, now H is called. I want to find all the child node of H. So I'm going to expand the tree in the needed structure alone. Okay, so in this place what happened? You have 3 possible moves for C. And out of 3 possible move, one move will be like when you swap 5, it will go back to the C state. Okay, I'm not going to do that. I take 2 possibilities alone. Okay, so you have 2 possible child. The repeat nodes are ignored here. Okay, since we are going to explore C, we want to find all the children of C. I'm finding all the children of C. That's it. Okay, so I can make a swap with 6 or I can make a swap with 7. Okay, when I make a swap with 6, your structure goes like this: 1, 2, 3, and 8, 4, 5, 7 will remain as it is, and here it is 1, 2, 3, 8, 4, 7 is swapped, right? 6 will remain as it is, 5 will remain as it is. Okay, now the nodes are created. 2 child nodes are created. I can name that as H, I, and J. Okay, so you have 2 child for H, that is I and J. What is the next step? Find the heuristic function for this node. What is the heuristic function? Compare this with the goal state and find all the misplaced tile. When you are comparing with the goal state, 1, 2, 3 is in same position. 8, empty cell 4, that is also in same position. 7, 6, 5 is in same position. So this is the exact goal state that is needed. There is no misplaced tile. So the heuristic function for this node is 0. And what happened here? 1, 2, 3 is in same position, 7 is in same position, 6 is not there in same position, 4 and again here you want a 7, but we have an empty tile. Here you want a 6. It is not there in the format, and 5 is in same format. So 3 tiles are misplaced. For J, the heuristic function is 3. Okay. So now come back to your searching algorithm. In your searching algorithm, what happened? When you are exploring H, find all the child of H, add it into the priority queue along with the priority of 0 and 3. Now when you are choosing the node with the minimum priority in the given priority queue is 0, and the node that takes it is I. What is the parental node for I? H. Okay, now I is the goal state and that is added to visit list, then the process stops. Okay, so we have to execute the process until the goal state is found and the goal state is explored. The goal state is added into the visit list. Okay, so once it is done, you're going to stop the process of this best first search. Okay, so this is how we have to proceed on a best first search algorithm. Now you could have got an idea of how to real-time application, like how to really apply a best first search in this 8 puzzle problem. And what is heuristic function? See, I take a place where the heuristic function is very low. Best first search goes ahead like this, right? So H is the place where the heuristic function is minimal. When I expand it, I reach to the solution faster. Okay, so that is the best thing that you have about this heuristic function. Initial nodes have a higher heuristic function, and when you choose a place with a minimal heuristic function, it leads to the solution faster. Okay, so first we know how to create a search tree, calculate the heuristic function, and how to apply our best first search algorithm into this tree structure. Fine. Thank you.